Okay, I think we'll get started then. Right now, it's a few minutes past. Probably have some more people trickling in throughout this, and that's fine. Would like to join everybody or welcome everybody that joined us today. Obviously, this is a little change up for us. Now we have been trying to do some live streaming throughout as we've been putting on these meetups. But now obviously we're a little more forced into it with all the circumstances and whatnot. Just would like to welcome everybody. If you don't know me, I'm Kurt Reckley. Myself and Branden and Timm co-organize Cloud Madison. As you're in this right now, please mute your mics. They should be coming in muted as you come in. We will probably have some spots for some time for some questions later on, or else throughout anytime, just put some questions in the chat, and we'll organize those and ask those for the when it's appropriate. So our sponsor for today is Integral. They are providing the technology, the Google Meet, for us right now. And obviously they've sponsored us throughout, been very important to the Meetup group. Our next online meetup, our next meetup will be again online. So we'll do at least May online, and then after that, we'll take a look at the situation and whatnot, and see if we want to do the June in person again after that. But for sure, we'll do May 4th. If you had saw the earlier meetups, invites to the meetup, this one was supposed to be sponsored by Logs.io. They're going to send a speaker in this topic here. Because we didn't know how this online was going to be set up, we wanted to do it sort of one time on our own first, but we do expect them to probably be the speakers for the next meetup on May 4th. But we'll certainly get that. We'll get that confirmed and get that out on the meetup site as an invite as we go along here. Regular news and notes. Obviously, with the coronavirus and everything, there's been a lot of conference cancellations. Google Next was supposed to be next week, I believe. That got changed to a virtual conference. Originally, again, supposed to be for next week, and then that got pushed off. There's many other conferences that are being pushed off. Now, I'm hoping a lot of these conferences, try to actually do a virtual conference with these. I think it's still important to get information from these conferences. Obviously there's always, typically good announcements and everything, but even all the sessions, as you start digging into technologies and whatnot, very informative. So I hope a lot of these conferences do come back as virtual conferences throughout the beginning part of this year. And like I said, the next conference was going virtual, and they haven't canceled the virtual yet, but although they did push it back, but they haven't announced when they're actually going to hold that as of yet. One of the other big things recently that's happened is Docker itself is regrouped as a cloud native developer tool community company now. Now, obviously, Docker itself has been very important to the ecosystem. Very fundamental to cloud native and the technologies there. Although the container part of that itself has been sort of brought out of Docker, but now that the company itself is hitting on some certain parts. The tool chain is one of the parts that it's trying to do. Also, I think it's trying to get into a little more security stuff. I do hope Docker succeeds as a company. Obviously they have been important to the whole ecosystem, even though now it's been sort of commoditized out of the actual critical path. Another important thing that's happened recently, Kubeflow is announced 1.0. If you're not familiar with Kubeflow, it's a way to bring in a little more of the machine learning, building and training and deploying machine learning type stuff in there. Now, obviously, there's services both within Amazon and Google itself that have sort of these managed machine learning. AutoML is Google's. I can't remember off the top of my head what Amazon's is at this point. But Kubeflow is a way so you have a little more control over that, the types of things that do it, and it's sort of the whole ecosystem there. So interesting to see where that goes in the future. Another announcement relatively recently is Splunk is sort of dives into the cloud native application monitoring. So think of an APM, into the application so you can see all stack traces and everything. But they're also claiming to get into the Kubernetes runtime itself to start to understand the performance of those orchestration systems as well and how they affect the overall application performance. Of course, they use all the buzzwords in there as well as using AI and ML, to bring out some insights into that. But ultimately, I think that's a space where I think, we do need to expand, and it starts to show a little more of the maturity in the ecosystem right now of some of these products now, targeting that orchestration layer itself, because that is ultimately all part of the one whole application as we go forward. So hopefully there'll be more announcements like that for some tooling around that sort of stuff. Today's speaker is Branden, Timm. He is, like I said, he is the other co-organizer of Cloud Native Madison. Again, if you want to ask a question during the talk itself, just put that in the chat. I'll ask those towards the end. I think at the very end, we'll open up all the mics and let people ask questions through that at the end. But with that, I'll let Branden take over.
All right, thanks, Kurt. Can everybody hear me?
And indeed.
All right. Second, let me take over here. Let me go full screen. Okay. So this is my talk, Container Runtime Security, a primer. This was originally given at Deep 608, which is a security conference put on by 80 Business Solutions back in February. So with the short notice and having to readjust here, I decided that I would give this talk here. It wasn't recorded at that conference or anything. So only people who were there would have seen this so far, but I think it's good content and should apply broadly, kind of no matter whether you're using Kubernetes or what. Is everybody seeing full screen?
Well, we're seeing both screens.
Oh, you're seeing both screens.
Yeah.
One moment. Let me see if this works better. How about wait?
Oh, both.
Technical difficulties. All right, let's see here. I'll try this one more time. Oh, I see. Okay. Let me just share my browser then.
That looks better.
All right, how's that?
Good.
Cool. Okay. So let's jump into it. For those of you who this is your first time, as Kurt said, I'm one of the co-organizers of Cloud Native Madison here. I'm an architect at Integral. For those who may not be familiar with Integral, we're a subsidiary of Enterprise Holdings, which is Enterprise, National, and Alamo Rent-A-Car. And we make software for the auto collision space. So our software is, online software as a service, web applications, kind of tries to sit at the nexus between insurance companies, body shops, OEMs, service providers, and all that to make their lives better, essentially. So I won't belabor that point too much, but we've been doing containerization since about 2015. And really for the last year and a half, 2 years have been into Kubernetes. And we largely have, sort of a microservice oriented architecture. I don't know how to, so we've been doing this for a little bit here. So just want to share kind of where we're at, or where the industry is at, when it comes to container native security. So, a lot of ink has been spilled, if you will, about how maybe containerization is somehow less secure than more traditional deployments. And certainly, if you think about a container as just being like a mini VM, that's not the right way to think about it. And in that case, it is less secure technically than a virtual machine. But really, I think a lot more of the kind of fear, uncertainty, and doubt, or the real risks around modern architectures is more so that we have modern CI/CD systems, and that deployments are ideally happening multiple times a week, if not multiple times a day. And so a lot of the things that traditionally you had more natural breakpoints for, easier to coordinate across different areas within your organization, from developers to security or whatever. We've been kind of forced into making sure we know how to automate those things, and admittedly, a lot of organizations don't do that particularly well. I would argue that with the right settings, that containerized workloads can be at least as secure, if not more secure, than traditional virtual machine based or bare metal deployments. So let's just start by kind of like framing the problem here. So for most organizations, prior to containerization, this is probably more or less what your kind of high-level application architecture looked like, right? You have some application, whether it's something that you wrote in-house or a vendor-provided application. We're focusing on Linux here, but most of these things generally apply to Windows as well. And you usually probably isolate an application per virtual machine, and therefore you have your own isolated guest operating system, your guest kernel, if you will, for that application. Between the application and that operating system, if you're following best practice, you're probably implementing some sort of mandatory access control. And so some examples of this in the Linux world are SE Linux or App Armor. That's kind of like the Red Hat based and the Ubuntu based flavors of the same basic premise. But all that really means is that mandatory access control has you define a policy around what a particular application is allowed to do. So if you imagine, if I have a web server application, I probably want to write a policy that says, okay, this process can read from a certain subset of the file system, like my config directory. It is allowed to make or accept incoming network connections. If it's a true web application and it's maybe turning around and calling something else, I might also allow that process to turn around and make its own outbound network connections. But the idea with that mandatory access control is that it gives you very, very fine-grained policy against which you can define exactly what an application should be able to do. And then going down a layer from there, you have a totally isolated guest kernel. So at that point, if an application is compromised or something like that, you still have, kind of a sandbox around that process, so that would prevent it from talking to, the application on the left and the guest kernel in front, the application on the right in the guest kernel. And so those are both kind of software layers of isolation and access control that we have. And then with virtual machines below that, then you also have a hypervisor. And of course, modern hypervisors tie into hardware extensions actually on the silicon of any modern computer to force another layer of isolation, so that even if for some reason the application was able to compromise the guest kernel, that application wouldn't be able to, at least, assuming there's no bugs in that hardware implementation, would not be able to kind of reach across and either disrupt or access memory or other pieces of important data that may be going on in another, application running in its own isolated guest kernel. So in the security world, right, the phrase you hear a lot is defense in depth, right? And you always want to make sure that you have as many layers of protection in place as possible, because it's really, really difficult, if not impossible, to guarantee that any one layer of security is always going to work. The kind of pejorative term that you hear used for that sort of thing is sort of the Death Star model. So you have one, super tough outer shell that you think will protect you, but it just takes one little vulnerability and now the whole thing is compromised. And so with this traditional architecture, you do have multiple layers of that defense in depth strategy. And if we look at a container-based architecture and what the fundamental differences are between that and a virtual machine-based architecture is, instead of having those apps isolated to their own guest operating system, now you have those apps sharing that guest kernel. There are still isolation layers within the Linux guest kernel itself to try to isolate those applications from each other. And that mechanism is largely referred to as Linux namespaces. And so all you really need to know about that is any sort of feature that the application needs to talk to the kernel to do, which could be networking, mounting file systems, accessing memory, doing inter-process communication. All of those things are isolated into a namespace just for that application, so that one app can't even see those things that another app is using, or vice versa. And so this is where, maybe that the naive explanation of, well, what is a container, what is a mini VM, comes from a little bit, because you have some levels of isolation, but you're not isolating at the actual guest kernel level. And so if those Linux namespaces controls can be compromised, now you have arguably less isolation between one app and another. So if the app all the way on the left is able to break out of its namespace and perform some privilege escalation and essentially become root on that guest kernel, now it can disrupt or steal data from those other applications running there. You do still have mandatory access control systems with containers. So you can run that with SE Linux or AppArmor and define what those are able to do. Of course, that's up to the administrator to enable those things. And the other thing I'll mention about both SE Linux and AppArmor is that they're fairly simple to use when you're using packaged kind of vendor software from an organization or a company that's sort of taking care of writing that policy for you. So if you're on Red Hat or Ubuntu and you have SE Linux or AppArmor enabled, they'll typically come with the right policies that in most cases are going to work just fine for that. If you're at an organization that builds your own software, however, you're going to need administrators or the developers themselves to define those policies and make sure that they're well tested. And so there's a little bit of a barrier there. And certainly I would say not every organization does that perfectly. But continue to go down that chart there, right? So you still have a shared guest kernel. Again, that's all software. Software has bugs, especially with most, or I should say with Linux in particular, being implemented in C. I mean, C is obviously still kind of the de facto language for systems programming, although there's a couple of languages that are starting to come out to challenge it. It's a great language for performance. It's a great language for directly interacting with hardware. However, it is susceptible to a lot of bugs like race conditions and or memory, accessing memory that's been deinitialized and being able to exploit things like that. And so when we talk about those isolation layers breaking down, the kernel and the software is probably actually the most likely place that's going to happen, usually via a bug that somebody's able to exploit. And then going down from there, you still have a hypervisor. You still have, hardware with virtualization extensions that should guarantee that any process running in a single guest kernel can access another. But again, because we're bringing multiple applications on top of the same guest kernel, that hardware virtualization extension isn't really doing much for us to isolate our applications from each other. I will say though, this has a lot of advantages, besides security for, developers and operations, right? So we can pack containers much more densely onto our hardware and therefore reduce costs because we're not getting that duplicative overhead of the guest kernel in every place. Containers are obviously extremely easy to package up for developers. Make it local development for developers very, very simple compared to the past when maybe a typical local development setup required running multiple virtual machines just to kind of simulate your development environment. And the other nice thing about containers, though, is that the resource allocation can be a lot more dynamic, right? So anybody who's configured a virtual machine before is familiar with, selecting how many CPUs, how much RAM do you want to give to this virtual machine. And any applications that run inside there are constrained to that as a maximum. Whereas in the containerized world, I can essentially guarantee a certain amount of resources, but if there's extra resources available in the system being underutilized, these containers can actually burst up and use that. So there's a lot of advantages to running containerized applications, and the question kind of becomes, well, how can we start to get some of that additional isolation into the containerized architecture that we had when we were isolating applications to a per VM basis? This is just a slide kind of showing again what those Linux namespaces are. So you can imagine those procs or processes in the middle. They're kind of, you imagine them almost like nested Russian doll style inside all these different namespaces. So the user namespace controls the user IDs and group IDs that process can see. UTS is a time namespace. Net is network. PID is the process identifiers, so that these processes can't even see that there's other processes outside of its own namespace. And MNT is there for disk access. So that's just kind of an example for people who haven't been exposed to the idea of Linux namespaces before. So the question is, how big of a problem is this really, this whole notion that an application is going to be able to sort of escape those software-based namespace processes? And, the answer is that, this does occur. It's obviously going to be dependent on every company or organization and sort of the industry they're in, the regulatory controls that they're subject to, the data that they deal with, as far as what's a tolerable number of vulnerabilities that come out in these pieces of software. But there's been something on the order of 20 plus sort of privilege escalation or namespace breakout vulnerabilities and sort of the guts of the container runtimes on Linux over the last 4 or 5 years. Now, obviously, software comes out with vulnerabilities all the time, and I'm not trying to say here that this is any more or less, frequently being exploited compared to other pieces of software that we typically see run in the Linux world. More just to drive home the point here that this does exist. This is not just theoretical. There have been exploits in the wild that would allow a compromised process within a container to break out and to go kind of wreak havoc on your system. And so that's essentially what this looks like. So, you got one exploited app running inside of a container on top of that same shared guest kernel. You may not be using mandatory access control, or maybe it's misconfigured, or maybe that was able to be defeated as well. That process is then able to escalate itself to a higher level of privilege. And then it can DOS or steal data or otherwise impact those other running applications with this sort of model. So we're going to transition quick to mitigation strategies. And so as a quick, kind of tangent, right? I mean, containerization as a concept is not new, right? It's been around for a very long time. BSD and Solaris had very similar notions to it going back a while, and even before that, there was similar ideas to sort of namespacing processes in isolation. But in the last 5 years is when it's really kind of come into the enterprise in a big way with Docker and with Kubernetes, emerging as the de facto ways that you kind of achieve these kind of architectures. And there's been a huge amount of experimentation going on within this space in terms of how to mitigate these sort of things. And so I'm going to present a couple different strategies today on how you can go about doing this. First, let's talk about what you get kind of out of the box. So with Kubernetes and Docker, you get what are called seccomp profiles. And essentially, seccomp is a way to limit the system calls that a certain process can make. So, by default on Linux, especially a process that's running as a privileged user, they can do pretty much anything, including things that you wouldn't want most processes to be able to do. Things like setting the system clock, changing device configuration. Seccomp is essentially a library that allows you to have the program go through a one-way transition into a restricted state where it can only make certain syscalls. And just to expand on what syscalls are a little bit for those who aren't super familiar with the concept, anything an application wants to do, for the most part, when it comes to, let's say, reading files or making network connections or all the things that applications have to do as they go about their business, they have to interact with the operating system to do that. And the way that they do that is that the operating system itself has this interface called the syscall interface. They look like function calls in any other language, but it's just the process requests down to the operating system to do something on its behalf. And so seccomp is a way to limit which syscalls those can make to only those that are really well protected, only those syscalls that are sort of namespaced, if you will. The problem though with seccomp is that it's a pretty blunt instrument. There's out of the box not a ton of customization you can do. You can essentially go one way into an extremely restricted state, where even maybe making outbound network calls would be disallowed, or you can kind of have it off. But we'll see in a moment that there's better ways to handle that. There are also AppArmor profiles available within Kubernetes and base Docker. So this is kind of a default mandatory access control policy that tries to find a good compromise between, disallowing the really obvious stuff that most processes are not going to be able to do, while still being fairly open, so that you don't have to do a ton of tweaking of that policy for common things that enterprise software wants to do. Those profiles can be customized, and that's essentially the same as what you would do running any other program on a bare metal Linux install, where you'd have to go to the you'd have to customize that for exactly the sort of things that your application needs to be able to do. And then Kubernetes brings in this notion of a pod security policy. And so all that is at a cluster-wide level, I'm saying I mandate that anybody who wants to run in my cluster has to have a minimum of this seccomp profile and this AppArmor profile. So that way, if I have something I'm trying to deploy into the cluster, and I haven't said that I am going to conform to these various security policies, I'll just get an error right back that says, "Hey, screw off! You're not secure enough to run in my cluster." And so this, works pretty well. The pod security policy is really easy to define. I mean, you essentially say, I require this and this, and that at that point, you're kind of done. But let's see here. So if we go beyond that, the first one I want to talk about is open source project called Kata Containers. Kata Containers is a combination of two pre-existing projects. One is Intel Clear Containers. The other is HyperSH's RunV. And the goal here was to bring back that hardware-assisted isolation to the container level. So let's see what this looks like. So on the left-hand side here, you have sort of the typical sort of process architecture of what a container really looks like. So you've got some process at the top, some application that's interacting with Docker Engine, Container D, which is essentially, it's just a layer of sort of what Docker is that's pluggable in terms of how you want to run the actual container on the hardware. And then essentially it goes down to run C, which is, again, a component that most people don't realize is a feature of Docker, but that's what actually takes care of running that container on your system, actually executing that container, doing all those things. On the right, you have Docker with Kata containers enabled. And so Kata Runtime is a different, again, pluggable API architecture, so that I can actually use a variety of different hypervisors on a per container basis to secure my system. And so the other nice thing that Kata Containers does is it tries to bring an extremely thin runtime, just enough you need for that security isolation, without having to run a really giant kernel. And so, they say that, their VM boot times are somewhere in the range of 500 to 900 milliseconds to actually start a container. So they're trying to make that really as thin as possible. So an advantage of this approach is that the developer experience remains largely the same. Developers who are creating containerized software don't really need to know anything about Kata Runtime, Kata Containers. To them, it looks exactly the same, but on an operations and a security level, you're getting that extra hardware-assisted virtualization to isolate in case you do have a bad process running in your cluster. And the other nice thing there is, kind of inferred, but software compatibility is really not a concern here, right? So again, going back to things like seccomp and AppArmor, those require some fine tuning of those profiles to make sure that what your process needs to do in the happy path, it is actually able to do without that policy being too restrictive. With these Kata containers, you don't really have to worry about that anymore. You should have the same compatibility as if you were just running a basic container. There are, of course, some limitations here, some trade-offs. So one is performance, right? I think most of us that have worked with virtual machines understand that although it's very minimal these days in most cases, unless you're way over allocating your resources, virtual to hardware ratio, there's still some overhead, and that's mostly going to be on I/O operations. Like anything in this space, you'll always want to test your applications to understand what does that performance penalty look like by going to virtual machines. And then the start times, like I said, they are minimal. However, if you really need really quick scale up, let's say you're using some sort of scale to zero kind of model where you're not actually running any copies of your application until a request comes in for it, and then you actually start up some containers to handle those requests. You're obviously going to have a lot more lag on those initial kind of cold starts. The other thing is that you can't just install this if you're using a managed Kubernetes service. So I think a lot of people out there, are kind of rolling their own clusters on their cloud provider or bare metal hardware of choice. But a lot of enterprises are, starting to get on these managed services as well that are available in pretty much every cloud. The three big ones probably are Azure, AWS, and Google, of course. But you can't just bring this to your managed cluster, right? Because this is kind of below the layers of control that they give you where you need to do something like this. And then finally, the hardware support is limited. So if you are rolling your own clusters, you have your own bare metal hardware, whatever, you can use this with Intel, ARM, and IBM. You can't put this on your shiny new AMD Threadripper, unfortunately. So a little bit of a hardware limitation there. The next one I want to talk about is a similar project to Kata containers, but tries to achieve similar things in a different way, and that's called gvisor. So gvisor is a user space sandboxing mechanism from Google, and what that means is this doesn't actually run in the operating system level itself. That means it's essentially another application running on top of the operating system, just like anything else. And what gvisor does is essentially implement a limited kernel, Linux kernel in user space. So something that looks like Linux, but actually sits on top of the real Linux and provides its own syscall interface up to the application it's running. And so by presenting something that looks like the Linux kernel to containers, again, many containers can run without modification, and gvisor can intelligently filter the interactions between the container and the true host operating system. And so it's really trying to attempt to provide that isolation that a virtual machine would give you without some of those limitations that we saw with Kata containers. And so the architecture essentially looks like this. So again, system calls are made by that application. That is compared to a list of acceptable system calls, but from gvisor. If it's not accepted, it's filtered, and the application just gets an error. The really interesting thing, though, is that in addition to filtering the system calls being made, gvisor actually re-implements a lot of those system calls in its own runtime that otherwise would be made to the Linux kernel directly. And if you recall what I was talking about with C, about there being a prevalence of bugs due to how low level it is and sort of all the kind of scary but very performant things you can do in C, gvisor is actually implemented in the Go language. And so Go, while certainly not as fast and not as easy to integrate with hardware as C is, it does have a lot of advantages when it comes to safety and security. So for example, Go has a lot of things that C doesn't have, like built-in bounds checks. So you can't accidentally access, say, an element of an array that's beyond the bounds of that array. You can't use there's no notion of uninitialized variables like in C. It's impossible to use a variable after it's been freed, unlike C. There's no stack overflows, and it has a built-in race detector as well to avoid those common bugs as well. So looking at this, we don't have the same hardware-assisted virtualization security features like virtual machines, but we also don't have the management compatibility and sort of resource constraints of nesting another VM for each container either. Because again, whereas with a VM, you need to statically allocate a number of cores and, amount of memory, that you want to give to that VM and therefore that container running within there, gvisor is just another process on the Linux kernel. And so much like a regular process or containerized process, it can kind of burst up within certain bounds or beyond certain bounds when there are or underutilized resources available. Let's see here. Let's go to the next slide. Any questions so far? Feel free to jump in or post them in chat. Okay, I'll keep going here. So just like Kata containers, gvisor has its own limitations, right? But basically nothing in the IT world or computer science world is without some trade-offs. So it's a little bit less flexible when you consider the syscalls that it allows than SE Linux or AppArmor. In fact, that's essentially a static list of allowed calls that they've re-implemented. So that makes it very simple, right? There's no manual configuration of any policies to define what your applications are allowed to do, but you're going to have to test your applications to make sure that everything they want to do is indeed supported by gvisor. And secondly, gvisor, of course, does have its own overheads, right? So virtual machines have certain overheads. Gvisor, as another process, kind of sandboxing your container, also, of course, has its own overheads. Just like virtual machines, that performance penalty is something that you probably want to measure directly with your own applications. It's going to be heavily workload dependent. Again, very I/O heavy applications are likely to see a bigger performance penalty. This is available on one managed Kubernetes service. Unsurprisingly, it is Google's Kubernetes engine, Google Kubernetes engine. So that is available with some managed services. You can also, of course, bring this to your own clusters if you're rolling your own clusters. So that's kind of the two different takes on sandboxing or virtual isolation of these processes that we're going to go over today. There is another one, however, that is called Falco, which takes a totally different take on this. Oh, wait, not that Falco. That Falco. When I presented this at Deep 608, Rock Me Amadeus played there. Apparently that's not working over Meet. So Falco takes a different approach to this entirely. So rather than sandboxing or filtering the syscalls that a container can make, Falco runs on every node that runs containers in your Kubernetes cluster, and then extremely efficiently captures the syscalls and the associated metadata along with that associated with that syscall. It then compares that syscall and all that metadata to a defined rule set. And if a rule has been violated, it will actually log that and then take any number of other actions that you want to configure about that. So this is not an enforcement tool. This is an auditing tool, essentially, auditing and alerting tool. However, you can integrate it with other systems to make it sort of a reactionary or an enforcing tool. So for example, if Falco sees that a process made an outbound network connection or that a user exec'd into a container, which you probably don't want to do in production because that means anybody who can do that can change the software that's deployed within that container itself, it can fire off an event. It'll first log it, but it could also actually send that event to something like a security logging system, a security control center. It could fire off an email to your security operations team. It could post in Slack. Even more interestingly, it could post a message to something like a messaging queue, like Amazon SNS or Google PubSub or RabbitMQ or whatever you want to run on-prem. And then you can really do anything you want with that. So one example is you could fire off a message from Falco into that messaging queue, and then fire that into a serverless function that maybe takes an action against that container as soon as it gets that to, say, quarantine or kill, or maybe even just profile what's going on inside that container. So by doing that, you're actually able to do essentially infinite number of things with this knowledge that Falco is giving you out of there. And the real other advantage over sandboxing or virtualization here is that it is, like I said, extremely efficient. In fact, you should see essentially no performance penalty in your instrumented application. And this is going to be a little deeply technical, but the Linux kernel has essentially within it its own virtual machine called the Extended Berkeley Packet Filter VM. it simulates a RISC processor style virtual machine and was originally developed to do things like packet captures. The reason that this can be so efficient as opposed to other tools is that all the knowledge around these syscalls and all the other stuff that we really want to be able to catch at a low level, all that information is inside the kernel and therefore inside what's called kernel space of memory. And for those who aren't familiar with kind of kernel space and user space, when an operating system starts up, it essentially has a hard sandbox between the memory that the operating system is allowed to deal with and the memory that user run programs are allowed to deal with. It's a basic security feature. The problem comes in is that all that data we want is down in kernel space, but obviously to do anything useful with it, like send an email about it or post a message to a queue about it, I need to get that information back up into user space. And that's what's called context switching. Context between kernel space and user space. And traditionally, you want to avoid that as much as possible because essentially every time you context switch, the processor itself has to do a lot of work to change those contexts. And then, so what you'll see is actually kind of this shadow performance degradation when tons of context switching has to occur just because of those context switches, and that can actually slow down your applications. So again, the eBPF VM being in the kernel means it can essentially just get alerted inside the kernel of all the information it needs and actually evaluate against that rule set inside the kernel. And then all it has to do in terms of context switching is when it finds a violation, it passes it back up to a process listening there, which is the sysdig Falco process. So again, extremely efficient, much lower overhead kind of per application than either the sandboxing or the virtualization features that we saw before. This is an example of what a Falco rule looks like. There are some macros in use in that condition. So essentially, some function calls that actually expand out to a little bit more code. But you can see that, and this is actually from the default rule set. There's not only a default rule set available with the Falco project, but there's many kind of open source or community contributed rule files as well. But this is, for example, how to make sure that somebody's not SSHing or execing a remote terminal into a container. And you can see the condition there almost reads like plain English. And then you can decide based on that condition what you want the output message to be, the priority, and then you can actually tag those as well. And all those, the priority and the tags are really just to give you some extra metadata so that you can easily configure what you want your responses to these kind of violations to be. And this is an example of what that output would look like. So it's cut off a little bit here, but you can see that in this case, a terminal shell was exec inside of a container. And then not only do I get that this happened, but I've got all kinds of additional metadata around that particular violation so that, this could be parsed out by a system that's looking for this in order to respond automatically. This could also come out in not in this JSON format here, but it could be formatted as an email message with the same sort of metadata in there, and maybe that routes off to a development team, an operations team, or security team so that they can actually follow up in whatever ways that your organization wants to. So when I gave this talk at Deep 608, I did a demo of Falco in action, where it actually was wired up so that when I execed into a container, it did fire off a message through PubSub and then route back to the Kubernetes API and actually killed that container that I was in. I forgot that I deleted that demo cluster and I was scrambling to get it up this morning, so I wasn't able to get the playbook fully implemented before I started this. But I do at least have this running in a live cluster here, which I can show you. Let me switch to this terminal. Okay, can everybody see the terminal?
Yep, we can see it.
Great. Okay. So I've got a basic 3-node Kubernetes cluster here. This happens to be running in Google Kubernetes Engine. And the way that Falco gets deployed is as what's called a daemon set in Kubernetes. So a daemon set is just a particular container deployment where it makes sure it runs one container, one replica of your container on every single node operating within the cluster. And so with a 3-node cluster, I've got 3 copies of Falco running out there, one per node. And what I'm going to do now is just kind of tail the logs across all of those different 3 replicas. There we go. Bring up another one here. So right now out here running, I just have this simple example container. This just runs a very simple web server that I'm not actually going to be interacting with at all. It's just really running out there as some container pod so that I have something to exec into so we can watch what Falco is actually doing here. So I can exec into this pod. I run bash. Okay, and we saw immediately that this notice, let me actually pull this out and prettify it for everybody. Okay. So we can see here the formatted output message with everything. We can see that got a notice that a terminal shell was execed in the container. We can see exactly the pod that was exec into, the command that was run, and some other additional metadata. I was logging in as root. So again, this is something that you can wire up so that this would be wired off to a messaging bus, and then you have your consumer look at that, and it would then be able to use this metadata to then follow back and say, all right, I don't want this to happen. Go either quarantine or kill or start profiling what's going on in this container right now because I'm seeing something I don't like. Okay. So a final set of recommendations here. So, like anything in this realm, it really depends on your organization, your company, the kind of data you're dealing with, the regulatory controls you have to deal with in terms of what is an appropriate sort of defense and depth strategy when it comes to container runtime security. At a very bare minimum, though, if you're running Kubernetes, you should probably, or Docker, you should absolutely be leveraging SecComp, AppArmor, and pod security policies to protect your Kubernetes workloads. That just gives you a base level of comfort, knowing that pods aren't going to be able to run in privilege mode, access system devices, and do the other kind of things that you really just almost never want happening on your system without a very well considered exception for that rule. If you are multi-tenant, in a highly regulated industry running untrusted code, so maybe you're running a cluster that you allow other people to develop code that you don't control into that cluster, I would absolutely be considering something like Kata containers or gvisor to provide that additional sandboxing and isolation around each one of those containers that are running out there. Whether you're doing either of those, I would consider running Falco to integrate that behavioral analysis into your security operations. So, you don't have to have Falco wired up to, a playbook that goes and kills, quarantines, profiles, anything. It's pretty interesting. And in fact, if an organization was going to start doing this, what I would start with is just let it run out there and start to get a baseline for what's even happening in your clusters before you start to wire up those reactions to them. It may turn out that your applications are doing something surprising that you weren't expecting. But either way, it at least gives you that insight into maybe how you need to define those rule sets or policies so that you can actually start to incrementally implement some automatic reactions when you see things that you aren't expecting. That's it. And with that, I will take questions.
So how mature is Felkel right now?
Yeah, so Falco is, I believe, a sandbox project. It's either sandbox or incubating within the CNCF portfolio. So I didn't mention it directly, but Falco is contributed from a company called Sysdig. For those who aren't familiar with Sysdig, they've actually been around for a bit now, and they kind of initially were building a lot of tool sets to do things similar to what it's doing now, where you're doing security or performance analysis from inside the kernel. And those mechanisms that they've developed for doing that, I think, are very, very strong and well tested, because they've been doing that for a long time, and they're very efficient at it. Back when, for those that have been kind of interested in the sort of Unixy performance analysis or debugging space for a while, maybe you're familiar with a tool called dtrace that started off within the Solaris operating system, and they kind of pioneered this concept of doing this very, very, very efficient sort of profiling from inside a Unix kernel. And Sysdig came out with their own kind of totally different implementation, but a similar capability within a couple of years after that, and that was probably the early 2000s, early to mid 2000s, if I'm not mistaken. So the technologies they're using to leverage this kind of to get those insights into what an application is doing are very mature, and in fact, Sysdig has paid commercial offerings on top of with capabilities in addition to Falco. I think it's called Sysdig Secure is one of them. They've actually put a really nice product together on top of these technologies that they're doing, and they're fully supported and all that. So as far as Falco itself, it is an open source system, and so I found out it's not always super straightforward to install and things like that. Again, it really depends on the kernels you're using and maybe the managed service you're using. But once you get it installed and running, it does seem to be really mature in terms of its stability, and I would trust it at least to do a production POC type thing. Any other questions? I will mention for anybody who's interested in this space, so this was kind of a micro view of sort of what one might call sort of the end-to-end container security space. For anybody who wasn't able to make our meetup last month, John Moser and Dan Plasik from AE Business Solutions kind of did a 30,000-foot view talk on kind of end-to-end container security. So I definitely recommend taking a look at that. It is out on our YouTube channel for Cloud Native Madison. They look at everything from starting development to you've got that thing running out in production. This was really more meant to be a deep dive into that all the way on the right. You've got something out in production. All of your other controls and mechanisms for securing that pipeline have failed. What is sort of your last line of defense for that running application on your clusters? So do encourage people to go check out that talk from last month, and maybe it'll help put some of the other things mentioned here today in better context.
Well, thank you for the presentation. It was very informative. And I think, if there's no further questions, I think we'll wrap it up for today. Again, we have been recording this. We'll try to get it out onto the YouTube channel as soon as possible. Again, next month we'll do something similar. Still determining what time. If this lunchtime worked well for everybody, let us know that. I think we may put out a survey just to see if this was a good time, or night would be better for the online stuff as well. But either way, thank you all for joining today, and hope to see you again next month.